Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone. So last class we were discussing how to prove this Subotovskaya's theorem. Okay, so essentially what the theorem states is that, so if we have a function, if we have a Boolean function, and now if we want to consider the formula size of that function, the minimal formula size of that function, then we can give a upper bound, we can give a lower bound on the formula size of the function based on a restriction. Okay. So, let epsilon be some constant. So, we saw that, so R n m, so R superscript and subscript m basically means all restrictions, okay, which leave m variables free. Okay. So, if we are looking at epsilon n, we are looking at all restrictions of n variable functions that will leave epsilon n many or epsilon fraction of the variables as free. Okay. So, the free variables can take any values, the remaining variables are restricted to be either 0 or 1. So, now what this is saying is that if I look at this restricted function, because of course, the restricted function is a smaller function, so it will have a smaller formula complexity. So, this theorem characterizes the expected formula complexity of that restricted function in terms of the formula complexity of the original function. Okay. And what it says is that it gets restricted by a factor of epsilon to the power 1.5. And we saw last time that showing that it gets restricted by a factor of epsilon is quite trivial, okay, because it is just counting the number of leaves that disappears. So, if we restrict if we restrict 1 minus epsilon many variables, then of course, those many leaves of course will get reduced. So, getting epsilon is easy, but the non-trivial part here is how do we get a better upper bound. And the idea that we kind of argued last time that we want to exploit is that we are considering formula over the De Morgan basis. And over the De Morgan basis, what we can argue is that, let us say if I have a AND gate, okay, and let us say one sibling of the AND gate takes a value 0, then irrespective of what the other sibling, what the other subtree looks like, the function evaluates to 0. Okay. For OR gate it is 1. So, we have actually proved this lemma last time, that if we consider a minimal formula for a function, okay, over, so this is actually over the De Morgan's basis of course. So, everything that we are discussing now is over the De Morgan's basis. So, if we consider a minimal formula for f, and if we look at any xi leaf, okay, any leaf labeled xi, then if we look at the sibling of that leaf, and if we look at the subtree rooted at that sibling, that cannot have another xi leaf. Okay. So, that cannot have an, well, I should say more precisely, cannot have an xi leaf. Well, if it has an xi, it has to be a leaf only, it cannot be an internal one, but yeah. So, it cannot have xi, and then we argued why this is true, last time we proved. Okay. So, now what we want to prove is that using this lemma, we want to give a restricted version of Subotovskaya's theorem. So, look at this lemma. So, we stated this lemma last time. So, here what we are saying is that if, let us say suppose I have a function with formula complexity greater than 1, okay, and if I restrict just one variable, okay, so one variable gets restricted to some value, remaining n minus 1 variables are free, then the formula, expected formula complexity is at most this 1 minus 1.5 by n of LF. Okay. So, how do we prove this? So, any questions? Okay. So, again, so the proof is not very difficult. Once you have this observation, which we showed last time, the proof kind of is quite obvious. So, let us try to look at the proof. So, what we will do is we will write we will write an expression for this left hand quantity. Okay. So, suppose I have, so what does this mean? So, what this means is that if I, so the expectation is over some variable, okay, and each variable can take a value 0 or 1. So, basically I can write this as 1 over 2 to the power n sigma I going from 1 to n sigma b taking a value either 0 or 1, that L f has a variable xi that takes a value b. Okay, so, this is just a notation that I am using. Okay. Huh? Which one? This one? No. So, there are it's an average, right. So, expectation means I am taking the average. Okay. So, I am looking at all possible variables xi, and for every variable I am looking at all the values that that variable can take, which is 0 or 1. So, I have a total of 2 n many choices, n variables and 2 values per variable, and I am assigning that value to that particular variable. So, for everything, and I am just looking what is the thing. Okay. So, it is just averaging over all these things. So, now I can rewrite this as, I will write this as L of f minus, okay, is xi is assigned the value b. Sorry. Okay. So, I am just adding and subtracting LF in this expression. Now, what we want to estimate is what is the value of this quantity. Okay. So, let us try to understand what this means. What this means is that if I take the formula for f, okay, and if I take some variable xi and if I give it some value b, then or basically what I would like to estimate is a little more than that. So, this is let us say I and this is over b. So, I would like to estimate actually this entire quantity. So, if I take a variable xi and if I set it to some value b, how much is the decrease in the formula size? Okay, how much is the formula size decreasing? So, any guesses how much? So, let us say forget about b for the time being, let us fix a b. If I assign a value b to a variable xi, how much will the size of the formula decrease by? So, let us give a lower bound. So, at least we want to say how much? At least the number. So, how many such leaves are there? So, we will have at least one xi leaf, right. So, there it will reduce by at least 1. Okay. But can you say a little bit more than that? If I consider this also, if I consider this summation also, so if I look at this particular expression over here, observe that, well, if I have a xi leaf, okay, whose parent is, suppose let us say without loss of generality an AND gate, and if I have some subtree over here, then if xi gets a value 0, okay, then Huh? Not only this gate can be removed, but any gate over here can be removed as well, right. If this gets a value 1, then only this gate can be removed. So, the point is this expression, okay, so for and if it is an OR, it is the other way around. If it is an OR and you can keep on removing everything, that is fine, but I am just trying to argue that in this part how much can I remove, at this level how much can I remove, okay, because I just want to give a count. Okay. So, here what this is saying is that if we have a structure like this, then for every xi variable, for every xi leaf, for every xi leaf, L of f minus L of f xi getting a value b, and if I sum this over b belonging to 0 1, this is at least equal to 3. At least 3 leaves would get removed, okay. And this is what gives us this 1.5 kind of a thing. 3 leaves basically for one value of xi, I can say that only that leaf will be removed, and for the other value of xi, some leaf over here and some leaf over here, total 3. Okay. So, now let us try to just plug this in back. So, we have this expression over here. So, this expression I can write as being greater than or equal to this. So, I have a minus over here. So, this will be less than or equal to L of f minus 1 over 2n sigma I times 3. Right. Yeah, and it is not just 3, it is actually 3 times Li. Okay. So, for every xi leaf I am removing 3 nodes, for every xi leaf 3 nodes are removed. So, this will be 3 times the number of times xi is present. Okay. For every xi leaf, 3 leaves are removed. Okay. So, I will have 3 times Li. So, this I can write as equal to L of f minus 3 over 2n, and sigma Li is nothing but L of f. Okay. So, this is equal to L of f times 1 minus 1.5 by n. Okay. So, this is a, so once we get this observation, this is easy. And where do we use the fact, where do we use this other lemma? Okay, so let us call this as lemma 2. So, where do we use lemma 2 in this observation? So, we are using lemma 2 as basically to take into account for duplicates, right. So, when I am counting that for every xi leaf 3 leaves are removed, I am using the fact that if I have an xi leaf, here I do not have any other xi leaf, right. So, that is where I am using the lemma. So, this has only some other nodes. Okay. Now, let us come back to the, so this proves lemma 1 over here. Now, let us say I want to use lemma 1 to prove this theorem. Okay. So, one way to prove this theorem would be that I will keep on applying lemma 1 in a iterative manner. Okay. So, I take one variable, I restrict it, I get this bound, and then again I restrict it, and I keep on doing this. So, let us say, so suppose I have f, let me call f as f of n, and then I have f of n minus 1 that I get by restricting one variable, then I have f of n minus 2 and so on. I will have f of m, okay, where m equals epsilon n. Okay. So, this is my sequence of functions that I get by restricting a variable at each step. So, now what I can do is I can apply lemma 1 iteratively, and if I apply lemma 1 iteratively, what I will get is, so basically at some intermediate levels I will get something like this, that well, expectation of sigma in R k minus 1 L f sigma is at most 1 minus 1.5 divided by what would be the denominator. So, the denominator is basically, so here I am restricting from k to k minus 1. So, the denominator is k over here times L of f. Okay. So, f is some k variate function. So, if I keep on doing this again and again, I will get this, but there is one problem with this application, and then basically what I would have is, if I just keep on applying this, I will get 1 minus 1.5 by k whole to the power whatever epsilon n, and that would give me a way to obtain this theorem. But there is one problem in this application. Can you see where it is? Okay. So, this application assumes something. What does it assume? Okay. So, here it assumes that the formula complexity is greater than 1. Now, what can happen is, I mean, one of these intermediate function can have a formula complexity maybe 1, it can also maybe have a formula complexity 0. Okay. I mean, that is possible, right? I mean, we do not know anything about these intermediate formulas. So, I can have a formula here which has a complexity, or I can have a function here which has a formula complexity as 1. So, therefore, this cannot be applied. Okay. So, will not work since lemma 1 assumes that L of f is at least 2. So, now we have to give a generalized version of this lemma. Okay. We have to give a lemma which would basically work for all functions irrespective of their formula size. So, basically that can be taken into account by just introducing a small constant. Okay. So, that is why this 1/3 actually comes. So, we will just introduce some what do I say, some flexibility when we give the bound. So, let me state another lemma which is, we have 2 here. So, let me call this as lemma 3. So, what we will prove is that expectation sigma in R n n minus 1 of L of f sigma minus 1/3 is at most 1 minus 1.5 by n L of f. I think one second, let me just verify this. Okay, yeah, L of f minus 1/3. Okay, and this is for all functions. or even for all formula sizes. So, how do we observe this? So, we will just show it in 3 cases. Case 1 is when L of f is greater than 1, then case 2 is when L of f is equal to 1, and case 3 is when L of f is equal to 0. Okay, so, let us look at the 3 cases. So, proof. So, if L of f is greater than 1. So, let us try to see what happens over here. So, the left hand side is expected value L of f sigma. Now, this is difference of 2 quantities. So, I can write this as L of f sigma. I can take the 1/3 minus I can take the 1/3 outside the expectation is less than or equal to what is this quantity. So, by lemma 1 we know that if L of f is greater than 1, this quantity is bounded by that L of f into 1 minus 1.5 over n, right. So, this is L of f into 1 minus 1.5 over n, and I have a minus 1/3. Okay. Now, what do I want? I just want to bring this 1/3 over here. So, that is quite easy. So, this I can write as less than or equal to L of f 1 minus 1.5. You want to turn the fan? I think the regulator. Yeah, yeah, 1.5 over n. So, this is I will just introduce some additional terms over here. So, what do I want to introduce? So, I have a minus 1/3 and I will introduce a, so this times this. So, this is 3 by 2 of n. So, plus 1/3 dot 3 by 2n. So, observe that this is a positive quantity, right. So, n is positive. So, this entire quantity is positive. So, this is greater than or equal to this, but doing this kind of will give me that this is equal to L of f minus 1/3. Okay. Just a small modification. Now, what happens if L of f equals 1? So, if L of f equals 1, let us look at both the left hand side and the right hand side of this expression. So, what does the left hand side evaluate to? So, if L of f equals 1, I mean I can again once again write this as expected value L of minus 1/3. What is the value? So, what does this evaluate to? Just think for a moment. What are we saying here? That L of f is 1, which means that I have a function which has only one leaf, for which there is a formula which has only one leaf, and that leaf is labeled by some variable. It can be any one of the variables. So, what does this mean? It means that, well, if I assign some value to that variable, only then the size of the formula decreases. If I assign value to some other variable, the size of the formula remains the same. Okay. And I am looking at the expectation. So, the probability that I pick that particular variable is 1 over n. Okay. So, if I pick that particular variable, so this expectation is basically 1 over n. If I pick that particular variable, the size becomes 0, and for all the other variables, so 1 minus 1 over n, the size remains 1. Okay. minus 1/3. So, this is 1 minus 1 over n minus 1/3 is 2/3 minus 1 over n, right. Now, what about the RHS? RHS is well, we know that L of f is equal to 1. So, 1 minus 1/3 is 2/3, 2/3 into this quantity is equal to 2/3 into 1 is 2 by 3 minus 2/3 into 3 by 2 of n is nothing but 1 over n. So, LHS is equal to RHS over here. Okay. So, here you kind of see why we picked 1/3. What is the role of 1/3 over here? I mean, why did suddenly we have this constant 1/3 appearing? Okay, you can actually pick some other, I mean, even for some other constant also it would work, but for 1/3 they are kind of becoming the same. And I will just leave the other one. The last case is when L of f is equal to 0. You can actually again verify that in this case also LHS will be less than RHS. Okay. So, if L of f is equal to 0, this side becomes minus 1/3 into this quantity. So, this is basically between 0 and minus 1/3, this RHS will turn out to be, and left hand side will be so the expected size would be, so this is 0 because L of f is 0. So, even restricting it becomes 0. So, this is 0 minus 1/3. So, 1/3. So, LHS is 1/3, RHS will be something between minus 1/3 and 0. So, RHS is greater than LHS. Okay. So, that completes the proof of lemma 3. So, now we are in a position to use lemma 3 to prove our main theorem. Okay. So, how do we prove the main result? So, what we have over here is, as I said, for any arbitrary k, okay, fine. What we have is if I look at a sigma and if I restrict from, let us say, k plus 1 to k, okay, L of f sigma minus 1/3 is at most 1 minus 1.5, yeah, we have a k plus 1 times L of f minus 1/3. So, I am assuming this is correct. Yeah, okay. So, basically what I am saying is consider an f, okay, which is already restricted to k plus 1 variable. Okay. So, I will basically I am doing it iteratively. So, first I start with n, then I, let us say I come to a level when it is restricted to k plus 1 variable, and now I want to restrict it to one more variable, I want to restrict it down to k. Okay. So, f sigma is basically a function which is restricted to k variable. Then by lemma 3 we have this observation. Okay. So, this is a direct application of lemma 3, and I can also write an expectation term over here. I mean, I can write this as E of L of f minus 1/3. I mean, there is no, I mean, yeah, so there is no probability over here. So, this is kind of like the same value. Okay. So, okay, and So, now if I do this how many times? So, I have to bring it down to epsilon n. Okay. So, if I do this many times, what I will get is expectation sigma r n epsilon n is in fact, let me just, so this should not be f over here, this should be f k plus 1. Okay. 1 second, let me sigma r n epsilon n L f sigma minus 1/3 will be how much times the value of L of f minus 1/3. So, how many times do I have to apply this? So, it will be 1, in fact, it will be a product over here each time I apply this. So, product of k going from m plus 1 to n 1 minus 1.5 by k, right. So, every time I do this, I am adding a additional multiplicative factor of this quantity. Okay. Now, what does this evaluate to? So, this actually again it is easy to see that yeah. And so, yeah, I mean I think I wrote somewhere over here that yeah, m is nothing but epsilon n. Okay. So, in fact, I can write here also instead of epsilon n, let me just use m over here, okay, because I am using m over here as well. Okay. So, this quantity, what does this evaluate to? Okay. So, I will use the inequality 1 minus x is, so what kind of inequality do I need to use over here? Okay. So, I have some products, okay, and I want to bound these product by some function of n and m. Okay. So, basically what I would use is the inequality 1 minus x is less than e to the power minus x, okay, for x between 0 and 1. So, this follows from Taylor's expansion. So, these are the first two terms of the Taylor expansion of e to the power minus f, everything else can be shown to be positive. So, therefore, this turns out to be, so this quantity over here becomes less than or equal to e to the power minus 1.5 by k, and because it is in the exponent now, this is summed over k going from m plus 1 to n. I take the minus 1.5 outside. So, e to the power minus 1.5 sigma 1 over k, k going from m plus 1 to n. So, what does this turn out to be? So, note that this I can write this as sigma n minus sigma m. of 1 over k. And what is e to the power sigma 1 over k? Okay. So, sigma 1 over k can be, I mean, one upper bound on sigma 1 over k is that it is ln of n, right. So, I will just use the inequality, okay, e to the power sigma 1 over k going up to n minus sigma 1 over k going up to m whole to the power minus 1.5 L of f minus 1/3. So, this quantity is upper bounded by ln of n. So, this would become e to the power ln n minus e to the power ln m is e to the power ln of n by m, okay, whole to the power minus 1.5 minus 1/3. So, taking the minus inside, I will have m over n. So, this becomes equal to m by n to the power 1.5. Okay. Now, what is m by n? So, m is epsilon times n. So, this is epsilon to the power 1.5. Okay. So, are we done? So, we are not quite done, because here I have a minus 1/3 term and I want to take that outside. So, this is this 1/3 term I can drop, because I just need a upper bound over here and this is only reducing. So, this is less than or equal to epsilon to the power 1.5 into L of f. Okay. So, L of f minus 1/3 is smaller than L of f, and now this is this 1/3 I can take outside the expectation. So, what I get is, okay, let me just write it over here. I get is expectation of sigma L of f sigma is less than or equal to epsilon to the power 1.5 L of f plus 1/3. Okay. So, I bring this 1/3 on the right hand side, and that gives us the theorem. Okay. Okay.